Dear students, today we are going to discuss experiment 4. So this is your experiment. So first one is VI characteristics, second one is DC to DC buck-boost converter and design of single phase inverter for PV system. And these three are hardware, and fourth one, that is grid connected PV system. Okay, this we are going to discuss now. So it is you can see here grid connected PV system synchronization and its performance analysis using MATLAB Simulink. So basically in this video, in this lecture, I am going to teach you the basic theory behind this experiment. Okay, so this is a block diagram. So here this is a PV power. Okay, this PV power, whatever may be generated, we are injecting into the grid. Okay, so as we know, PV, it is going to give a DC power, right? So here this is a PV. After this one, actually, whatever may be the, say suppose in generally what we are going to do, whatever may be the voltage, suppose grid voltage is 230 RMS voltage for single phase. Its maximum value is 325, that is VRMS into root 2. So whatever may be the voltage is there, that is 325. We are going to choose the DC link, that is whatever may be the voltage we are going to generate here. That is, suppose we PV panel voltage is, say suppose 40 volts. Okay, that is a maximum voltage at MPPT. At MPPT, the voltage will be, say suppose 40 volts. So in order to inject here, we require a DC link voltage of more than 325. Okay, then only power will flow from PV to grid. So in such condition, say suppose 325. Okay, 325 means how many panels I have to use? This is 325 divided by 40. Okay, means at least I need to use minimum of 9 panels. Okay, in case if I am going to use 5 panels, then is it going to inject? No, it is not possible. Okay, because power will flow from high potential to the low potential. So in such conditions, what we are going to do? We are going to boost the voltage. Okay, what I will say, suppose I have connected only 4 panels, then it is going to give only 160 volts. In such condition, we are going to boost the voltage. And then we are going to inject the same into the grid. Okay, so this we can able to do in two ways. One, we can able to do, we can convert this inverter itself as a boost converter. This is one way. This we call it as a single stage. Okay, or we are going to simply convert this DC into AC, and we are going to use one transformer here, and we are going to step up. Okay, then we are going to inject. Second way. And third way is, we can able to use a DC to DC boost converter. This we call it as a two-stage. Okay, earlier one which we have discussed is a single stage one. Okay, where we are going to convert DC to AC, and then we are going to use a transformer, and we are going to inject into the grid. That is a single stage one. In this one, in two stage one, what we are going to do, whatever may the 160 voltage is there, that we are going to boost the voltage to 400 volts, like that. Okay, in generally for single phase, we are going to use a DC voltage. We are going to maintain a DC voltage of DC link voltage as 400 volts. Here this is a 6 VDC. Okay, 400 volts we are going to maintain. Okay, this 400 volts DC we are again converting into the AC, and we are going to inject into the grid. So this inductor will be acting as a filter, and at the same time, that is, sir, what actually we are injecting? We are injecting current or voltage. Voltage is fixed here. Okay, grid voltage is fixed here. So we are injecting actually the current. Okay, so this for inductor, for current, which element we have to use, capacitor or inductor? obviously it's inductor. Okay, so inductor will not allow sudden change in current at this. So this act as a, so that's why we are going to use as a this inductor, and this will act as a filter actually. Okay, fine. So let us once again explain each and every stage in this one. So here we will be having a PV. So now I want to inject a maximum power. Okay, so as we know, power transfer theorem states that whenever the load side resistance is equal to the internal resistance in Thevenin circuit, then we can able to inject maximum power, or we can able to uh, transfer power, maximum power. So the same rule is going to apply here. Okay, so in this way, so here we are going to use a MPPT technique, maximum power transfer technique. So actually here tracking technique we are going to use. Here we are going to use PO, perturbed observation. In this method, so we try to calculate the power for each stage. For voltage, we are going to change. Again, we are going to change the position. Again, we are going to calculate the power. So it is going to compare the previous power. If it is greater than, then again it is going to change its position. So how actually it is going to change the position? By changing the duty ratio. That's it. Okay. Since it is a DC to DC boost converter, you will be having the duty cycle, right? So that duty cycle it is going to change. That's it. So it will try every time, it will try to compare the previous result, and it will try to change the its duty cycle. Okay, its alpha value. So like this, wherever you are going to find out the maximum one, then it will stay there and it will try to oscillate. It will not stick there. Okay, it will try to oscillate. Okay, it will try to oscillate. Fine. So this here we are in between PV and DC to DC converter. We are going to use a capacitor. This will not, what is the property of capacitor? It will not allow sudden change in voltage. Okay, so and then it will act as a filter also. Okay, because this is a DC. In case any AC signals are there, then it will try to minimize. Okay, it will try to filter out those AC components. Fine. So this block is over. So to find out the MPPT, what we required voltage and current, so that we can able to calculate the power. Okay, power is equal to V into I. Since this is DC voltage, okay, so you will not see any power factor here. Only voltage and current you are going to get. Okay, fine. So from this one, we have calculated the MPPT, and we are trying to inject the same. We try to uh, abstract maximum power. Fine. So now we are going to get a boosted DC voltage here. Okay. Then this is called a DC link voltage. Okay. We call it as a DC link voltage. Generally, we are going to term it as a VDC. Okay. General terminology, we call it as a VDC. Okay. This is a DC link voltage. So we try to maintain this DC link voltage as constant. How much? 400 volts. Okay. As earlier we have discussed, we are maintaining 400. Sir, why 400, sir? Because we have to maintain a voltage more than this 325. What is our maximum for single phase? It is 230. Maximum voltage is 325. So we want to maintain a voltage which is greater than 325. Then we are going to take nearly 400 volts. Sir, can I use 350? Yes, you can able to use a 350. Sir, can I go for 500 volts? Yes, you can able to go for 500 volts also. Thing is, we have to make a trade-off between this voltage. Okay, so that is, if you take more higher voltages, that is 500, 600 like that, then your switches has to block that much voltage. Okay, so while blocking also, we are going to face the switching losses. So that's why we try to reduce it. At the same time, we cannot reduce less than 325 also. Okay, otherwise it will not inject. So that's why we are using 400 volts. Okay, so 350 also we can able to do. Yeah, 350 also you can do, but your total harmonic distortion will be profile will be very poor, okay, when compared to the 400 volts. So fine. Next, this here DC link is DC power, and we try to convert this DC power into AC by using a inverter. Okay, so here what we have to maintain? One is 400 volts we have to maintain. We have maintained it. At the same time, whatever may be the power generator is there, it has to synchronize with the grid, because this is not a standalone process. Okay, in standalone, simply we will use a sinusoidal pulse width modulation, which we have done it in the previous video, how we have done it single phase inverter. For that one, you just give a all this setup, then it will be sufficient. The problem here is we have to synchronize it with the grid. In order to synchronize with the grid, we can able to use a PLL, or else some other technique where we are going to find out a unit template, that is sine omega t. Okay, sine omega t we are going to take, and then to this DC component we are going to multiply the sine component, then it will become a sine wave. Okay, suppose 5 is there, 5 is a 5 sine omega t is there. In 5 omega sine omega t, 5 is a DC component. Okay, sine omega t is a AC component. Clear? Which we have learned in our basics, that is in AC circuits, right? So like this here, we are going to convert the DC component into AC component by using this vector. Okay, so meanwhile in this process we are trying to maintain the VDC as constant, and we try to generate the pulses, and these pulses we are going to maintain this as a DC link voltage at 400 volts, and at the same time whatever may be the power generated, that is current component, it will be in synchronous with the grid. Clear? So this will be, inductor will be acting as a filter component. Okay, so this is a brief theory about the experiment number 4. Okay, so in next lecture we will discuss, we will try to discuss the MATLAB. Okay, the simulation file we will try to discuss. Okay, so what actually you have to do in that one, what parameters you have to calculate, what is the input power, what is the output power, what is the efficiency, what is the THD, how to calculate the THD, which THD we have to calculate. Okay, what should be the THD, and as per the standards, what is the THD value, whether we are following the standards or not, we will see all these things. Okay.